What if your rover could do more than drive? In this project, we'll give it vision. Using a Raspberry Pi camera, simple AI detection, and motor control, your robot will track colors, follow targets, avoid obstacles, and react to visual markers. You've already built the key pieces of an intelligent robot: circuits that sense, motors that move, code that makes decisions, and networks that connect systems. Raspberry Pi camera work added vision, so the robot can interpret what it sees. Project 16 brings those skills together into one complete AI rover system: seeing, thinking, and driving. This rover is more than a car with a camera. It runs a feedback loop. The camera captures the rover's view: colors, shapes, markers, or obstacles. The Raspberry Pi uses Python and computer vision to turn those images into useful information. Then the code chooses a command, such as forward, stop, turn, or adjust course. The motor driver turns that command into wheel movement. As soon as the rover moves, the view changes and the cycle starts again. That loop is what makes the rover feel responsive and intelligent. The rover can be understood as four connected systems. The Raspberry Pi is the brain. It runs Python, reads the camera, processes vision, and decides what to do next. The camera is the rover's eyes. Turning the real world into image frames the code can analyze. The motor driver is the muscle controller. It takes low-power signals from the Pi and safely switches the higher power needed by the motors. The chassis, wheels, motors, and battery make the robot mobile and self-contained. As you build, keep power wiring careful and secure, because one loose connection can affect the whole system. Another way to picture the rover is as a pipeline from pixels to action. The camera captures frames from the robot's point of view. Each frame is processed to find useful clues, such as a color, object, face, or marker. Those clues are not movement yet. A decision rule gives them meaning. If the target is left, turn left. If it is centered, move forward. If something is unsafe, stop. The Raspberry Pi sends the chosen command to the motor driver, which powers the wheels. That chain is how vision becomes motion. Motors need more current than a Raspberry Pi can safely provide, so the Pi should only send control signals. The motor driver does the heavy lifting. It uses separate motor power, switches current to the motors, and helps protect the Pi from voltage spikes. Direction pins decide whether each motor turns forward or backward. A PWM signal controls speed by rapidly pulsing power. Always connect a shared ground between the Pi and the driver, but never power motors from the Pi's 5-volt pin. Wire carefully, then test one motor before testing both together. Before you trust the rover's vision, treat the camera like a sensor, not just an accessory. Mount it at a useful angle, aimed where the rover needs to make decisions. Open the live feed and confirm the target is visible, centered, and in focus before connecting detection to motor movement. Next, check the lighting. Color and object recognition work best when shadows, glare, and sudden changes are limited. Finally, choose image size deliberately. Smaller frames process faster, while larger frames provide more detail when accuracy matters. Color tracking is a simple way to turn camera data into movement. The rover filters the image for a chosen color range, such as red or blue. The matching pixels form a blob, and the program estimates its center point, called the centroid. That X position becomes the steering signal. If the centroid is left of center, the rover turns left. If it is right of center, the rover turns right. If it is near the middle, the rover drives forward. As the blob gets larger, the target is closer, so the rover should slow down and then stop. At this point, the camera is not just following a line, it is watching for meaning. A detected face, sign, QR code, Aruko marker, or colored stop symbol can become an instruction. For example, the rover might see a red stop card, slow down, and stop before it gets too close. The same idea can trigger a turn, a sound, or a waiting behavior. Distance can be estimated roughly from image size. As the marker appears larger, the rover is likely closer. This works best with simple, high-contrast markers, because clear visual patterns are easier to recognize reliably. Target following is like keeping a ball in the middle of your view while you walk. The rover checks where the target appears in the camera image, then makes small corrections. If the target drifts left, it turns left. If it drifts right, it turns right. The target size gives distance clues. Small usually means far away, so the rover can move forward. Large means too close, so it should stop or reverse. Good following should not be jerky. It uses limited speed, gentle steering, and constant checking. The camera does not directly drive the motors. It produces facts. A target is found, the target is lost, an object is too close, or a marker appears. Decision logic turns those facts into actions. A state machine is a clean way to organize that behavior. In search mode, finding the target switches the rover to following. Losing the target returns it to search. Seeing an obstacle switches it to avoid or reverse. A stop marker has higher priority than color following, so the rover stops even if the target is centered. Clear rules make the robot's behavior predictable. A clean rover program follows the same pipeline every time. First, initialize the hardware, the camera, motor pins, and required settings. Then the main loop repeats. Capture a frame, run detection, and turn the result into an action. If the target is left, steer left. If it is centered, move forward. If nothing is found, search slowly. This logic can start as simple if-elif checks, then grow into a state machine as behavior becomes more complex. The key safety habit is always the same. When the loop ends or an error occurs, stop the motors and release resources. When an AI rover behaves inconsistently, don't guess. Run controlled tests. Change one factor at a time, starting with lighting. Bright, dim, shadowed, and mixed indoor light. Then test the camera angle, including positions that are too high, too low, tilted, or partly blocked by the rover itself. Finally, test speed, because fast movement can blur images or make reactions arrive too late. For each run, record the setup, detection success, and notes. Then compare results to see what actually improves reliability. Once the rover works at a basic level, improve reliability one change at a time. Start by tuning vision settings, such as color thresholds, confidence levels, or marker size rules, so random objects are ignored. Then add stability checks, like requiring the same target for 3 frames before the rover moves. During tracking, slow the motors down. Speed turns small vision errors into big movement errors. Finally, make the program explain itself. Print messages, draw bounding boxes, and show center points and confidence scores. Use a tune, test, observe, improve loop until the behavior becomes predictable. Project 16 brings the full robotics journey together. You connected camera input, computer vision, decision rules, and motor control, so the rover could respond to what it sees. The same pattern appears in delivery robots, warehouse vehicles, smart cars, and assistive tools. As you move into Module 6, focus on testing, improving, and presenting a reliable robot system.